Okay, so this is part one of lesson 2.1, Newton's laws. Our learning target for today is I can review Newton's three laws of motion. At the end of this lesson, you'll be able to define what a force is, distinguish Newton's laws, and relate Newton's laws to everyday life. So, what is a force? A force is essentially anything that is a push or pull on an object. So I can push a desk or I can pull a desk. They both represent a force. The units for force are Newton, which is named after Sir Isaac Newton, the guy who discovered gravity and did work on forces. How we label Newtons in a shorthand notation is a capital N. That means if you are writing a lowercase n, that is not considered Newtons and is therefore wrong. So please be sure that you are in fact writing this capital N here, okay? That's really important. And an alternative unit for a Newton, or for a force rather, is kilogram meter per second squared. Okay? I know that seems like a mouthful, but you'll see why in a second. So a Newton is equivalent to a kilogram meter per second squared. So if you recall, a kilogram is the unit for mass. That's what we use in physics class. Then we have this meter per second squared guy right here. That refers to an acceleration, if you recall that from kinematics, okay? So meter per results in this division line because it is a distance divided by time squared, right? So distance is meters, and then it's divided by seconds squared. So we say the word per to indicate that. As you notice right here, I have kilogram, right? In this empty space, I have kilogram meter per second. Well, given that I do not have a division sign there, or excuse me, the word per, I do not use division. And I simply do not have subtraction or addition. So therefore, the only thing that I'm left with in terms of operations is the multiplication symbol. It is a mass times an acceleration, and thus that is how we get a kilogram meter per second squared. Most times you'll only see this unit for force like once in a blue moon. Like all the other times, they'll just use a Newton instead. Okay? So, Newton's first law. All right, so you've probably heard the first part, but the second part is definitely going to be new. So there's two main pieces that have to be included, right? And this, like I said, it was part of this new part that you're hearing for the first time. Okay, so oops, let me undo that. So this is an object at rest stays at rest while an object in motion stays in motion in a straight line at constant velocity, which is not written in, so I wrote it in there, unless acted on by an unbalanced force. Okay, this is a pretty big deal. So like I said, you probably heard the first part, an object at rest stays at rest, an object in motion stays in motion, but the big key idea is here is that it has to be going in a straight line and it has to be going at a constant velocity. Um, and the only way that these types of motion change is due to an unbalanced force. Okay, and that should make sense because we learned that an acceleration is two things. It's either a change in velocity or it is a change in direction. So therefore, if it is not going in a straight line or it is not traveling at constant velocity, clearly it has to be accelerating. And so hint, 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 an unbalanced force refers to an acceleration. Okay? If you look at the animation, you have a guy in a truck. The truck comes to a complete stop, right? I drew this arrow. You do see that this individual wants to keep going, and this is really, really important in real life. Okay? This idea of if I come to a stop very quickly, what does the objects in the car want to do? All right, so if we go to the next slide, right, it says Newton's first law check-in. Why is it so important for us to wear a seatbelt when we are in the car? Well, when the car comes to a complete stop, right, very suddenly, your body wants to continue traveling in that straight line, just like in that previous animation. But our seatbelt is what holds us back and prevents us from being ejected through the windshield. So, for example, if you're sitting in the back seat, especially that middle seat, if you're not wearing a seatbelt and that car comes to a sudden stop very quickly, your body wants to continue moving and you will most likely become a projectile, an object that gets shot through the windshield. Okay, for those of us who are sitting behind the passenger or the driver's seat, If you're not wearing a seatbelt, you're going to smash your body into those seats. And while that seems kind of insignificant, that's a problem because uh, your body is making contact with the seat. So that's one type of collision right there. So it externally hurts your body. But also because you're doing that, you have an internal collision going on with your body, like your organs and the inside of your body. So that's very dangerous. So overall, it's really important for us to wear a seatbelt in the car. If you notice in this picture right here, this lady, she's wearing her seatbelt. Like what it does, it kind of catches her. Here she's doing the not correct thing, right? So she doesn't have a seatbelt on, so no seatbelt. So I'm going to just label that SB. And then look what happens. She goes right through the windshield, even though there's a steering wheel right in front of her. So even if you are the driver, that doesn't mean that you can't still fly out of the car, okay? So overall, Newton's first law tells us, hey, it's really important to wear a seatbelt because we will fly through the windshield because our bodies simply just want to keep going in a straight line, okay?